today's topic is nonlinear separable programming problem. Now, separable programming problems are a special kind of nonlinear programming problems in which the nonlinear objective function and the functions involved in the constraints are separable in nature. Separability means that a function, if the function is separable, then the function can be written as a addition of several terms where the individual terms are the functions of single decision variables. Mathematically, we can say that if a function f of decision variable f(x1), x2, xn is said to be separable if it can be written as f1 x1 plus f2 x2 sum of n number of functions of individual decision variables. Here I need to say that if function f is nonlinear function, the functions f1 that is a function of x1, f2 the function of x2, these are the functions, it could be linear, it could be nonlinear as well. Now, the way we are handling the separable programming problem, the basic principle is that we just express the nonlinear functions fi, xi as the combinations of linear functions, so that a nonlinear programming problem will be transformed into a linear programming problem. And for solving the linear programming problem, we have the simplex algorithm, and with the restricted conditions we can solve the simplex algorithm for handling the separable programming problem. Now, this is the basic idea, and one thing is needed for separable programming problem solution, that for individual variables, that is decision variable xi, we should have the lower bound and the upper bound where I is equal to 1 to n. Now, let us consider a general nonlinear programming problem, that is maximize or minimize f(x) subject to gjx greater less than is equal to bj, say, where there are m number of constraints are there, and x is the decision variable and x could be a vector with n components. Now, f(x) and gjx are the nonlinear functions. Now, as I said that for the separable programming problem, the objective function f(x) and the constraint functions, that is gjx, these are separable in nature. Therefore, the same problem, the nonlinear programming problem, can be written in separable programming problem in the way that is maximize or minimize. f(x) is the function of n number of variables which can be written as the separable functions. That is why we can write summation of I is equal to 1 to n fi xi, where small xi is the ith decision variable and the constraints would be summation I is equal to 1 to n, m number of constraints are there, that is why gij xi less than is equal to bj, where j is equal to 1 to m, and here xi's are all greater than equal to 0, that is a non-negativity constraints, that is for I is equal to 1 to n. Then this is the format of a general separable programming problem. All right. This is the general separable programming problem. Now, how to handle this problem? Now, for solving this problem, what we do, as I said, the basic principle is that we will just express individual nonlinear functions, that is fi's and gij's, as the combination of the linear functions. Thus, we need to know that two things we need to know. One is that when a function will be said as the separable function, or otherwise how a function can be expressed in the separable form if it is possible. And the second thing is that how a nonlinear function will be expressed as a combination of the linear functions. That is why let me detail both the things one by one. The first is that how to construct a separable function. Now, as I said that let me consider one function of two variables f(x1) x2, this is equal to x1 square minus 2x1 say x2 cube minus 3x2. Now, this is the function of two variables. Just see, we can write down this function in the form f1 x1 plus f2 x2 very easily, because it could be, we can separate the functions f(i's) for the function of xi's, where f1 x1 is equal to x1 square minus 2x1 and f2 x2 is equal to x2 cube minus 3x2. Okay. But if we consider a function f(x1) x2 as x1 square plus x2 square plus sine x1 plus x2. We cannot write this function in the form of f1 x1 plus f2 x2 because of the involvement of sine x1 plus x2. That is why this function is not a separable function. That is why separable programming technique is not applicable for such kind of function involvement. Let me consider another function, say fn x1 x2 is equal to x1 x2, the multiplication of x1 and x2. Though it cannot be directly written in the form of f1 x1 plus f2 x2, but if we simplify some other way, then we can write in the as a summation of separable function. Just see, let me consider one variable y1 as half of x1 plus x2, and let me consider another variable y2 as half of x1 minus x2. If we just write down in this way, then very easily we can write down f(x1) x2, that is given to us x1 x2 as a function, separable function of y1 y2. How? Simply we will write y1 square minus y2 square, then that would be x1 x2, and certainly this is the function of y1 plus function of y2. Thus, this function is the separable function. Thus, we can conclude that the functions which are nonlinear functions which are involved in the objective function or in the constraint, if this is in the form of separable function, then only this our methodology which I am going to describe is applicable for such kind of problem. Now, the next, how to handle, how to convert the nonlinear function into the separable form, that is into the combination of the linear function, that part I am going to tell you. Let me consider a function like this. For this thing I will consider only the single variable function, say f(x), because then only I can draw the function easily. The same idea can be extended for a number of variables x, and this is the function f(x). Now, if I consider this function in this way, now as I said, for the separable function, then the for the separable function, the lower limit say L and the upper limit say U is given to us. Then just see, we can express the nonlinear function in a combination of linear functions. Let me just describe geometrically first, then I will go for the mathematical expression for this. Now, let me partition this interval, LU interval, with r plus 1 number of grid points. How? This L would be is equal to x 0, x 1 would be is equal, x 1 is the next, x 2 is the next point. In this way, if I just proceed, U would be is equal to x r, and this is the previous point x r minus 1. Now, how we can express the C? We will consider the point x 0, we will consider the point x 1. In this interval, we will just add f x 0 and f x 1, then we will get a straight line. Thus, I can say within this interval, then function can be expressed as a linear function instead of a nonlinear function. In the interval x 1 and x 2, this can be written, the function can be expressed in this way. Similarly, for the next interval, function can be expressed, and this is very clear that if I consider the combinations of all such functions together, then that can approximate the nonlinear function f x very easily. And this is to be noted that if the number of grid points are more, rather if the points are very close to each other, then the approximation we are making, that approximation will be the best approximation. Now, how mathematically we can express these things together, just let me see. How I have written the grid points? I have written the grid points as x 0 lesser than x 1 lesser than x 2. In this way, x r minus 1 x r, that means r number of partitions we are having, and L is the lower limit and U is the upper limit of this function. That means the function f x for the decision variable, not for the function. Thus, the function f x is defined within the range L to U. Now, if this is so, let me consider the k n plus 1th subinterval. Now, any point x, k plus 1 is subinterval means the interval x k plus 1. Any point x in between x k and x k plus 1 can be expressed as the linear combination of x k and x k plus 1, all right. Now, where we know for the, if we consider the linear combination, lambda must be in between 0 to 1. Now, I can write down this expression as lambda k x k plus lambda k plus 1 x k plus 1, where I want to introduce the lambda coefficient with the k index, because I will extend this idea further, just I will explain in the next. Just see what is the condition here, lambda k plus lambda k plus 1 must be is equal to 1. And what is the next condition? Lambda k and lambda k plus 1 both are in between 0 to 1. Thus, if we have one interval x k to x k plus 1, any point x can be expressed as lambda k x k plus lambda k plus 1 x k plus 1. Now, let me extend this idea for the 3 intervals. That means, I will consider the interval x k plus 1, 3 grid points, and the next interval as well x k plus 1, x k plus 2. Then any point in between x k to x k plus 2 can be written as lambda k x k plus lambda k plus 1 x k plus 1 plus lambda k plus 2 x k plus 2, with the condition lambda k plus lambda k plus 1 plus lambda k plus 2 is equal to 1, and with another condition that lambda k plus 1, lambda k plus 2, these are all in between 0 to 1. Now, once we are expressing x which is in between x k to x k plus 2, then that if it is can be written in this way, then certainly either x is in within the interval here or the x is here. That is why lambda k plus 1 and lambda k plus 2 all cannot be simultaneously in the positive level. Either if x in between xk to xk plus 1, we will have lambda k and lambda k plus 1 positive, or if x is in the interval xk plus 1 and xk plus 2, then lambda k plus 1, lambda k plus 2 is positive, but here lambda k plus 2 is 0 and here lambda k is 0, because x cannot lie simultaneously in both the intervals. I am expressing x in terms of 3 grid points xk, xk plus 1 and xk plus 2. What is my objective? My objective is to express the function f x in terms of r number of linear segments, r number of linear functions. That is why first let me analyze the point, the x which are lying in the respective partitions. Now, we have considered 2 points, we have considered 3 points here. If I extend this idea further, then for r plus 1 number of grid points, that is, if we consider all grid points when x is lying in between x naught to x r, any x can be written as x is equal to lambda 0 x 0 plus lambda 1 x 1 plus lambda 2 x 2. In this way, I can write it is lambda k x k, k is in between 0 to r, where summation of r is equal to k, lambda k is equal to 1. Not only that, individual lambda k's are greater than equal to 0 and lambda k's are less than as well, equal to 1. And another condition we should impose, that since x is a point in between x naught to x r, x must be in either of the partitions. That is why x cannot be simultaneously lie in 2 partitions at a time. That is why we should impose the condition here, at least 1 or no more than 2 lambda k's are positive. Not only that, if 2 lambda k's are positive, then they must be consecutive. Because we are considering the partition x 0, x 1, x k, x k plus 1, in this way up to x r. If x is here, then lambda k and lambda k plus 1 will be positive. If x is here, then lambda 0 and lambda 1 will be positive, other will be 0. In this way, we can write down the function, we can write down the decision variable x in terms of r plus 1 number of grid points. The similar idea, the same idea we will extend to express the function f x in terms of k r plus 1 number of grid points. Just see in the next how I am expressing that fact. Let me consider again the whole interval, that is L to U, where the function f x is defined and we are considering the grid points x 1, x 2, x r minus 1, etc. Now, again we are considering the k plus 1th sub interval, that is x k to x k plus 1. Say this is the function for us. This is x k, this is x k plus 1 and this is the function here. Alright. If this is the function here, I am expressing the function in this interval as a linear function. That is why what we will do? In this interval we will just draw a line between 2 points x k f x k, x k plus 1, f x k plus 1. What would be the equation of the line? In other way we can write it as f x is equal to f x k plus x minus x k divided by x k plus 1 minus x k f k plus 1 minus f x k. Just I have simplified the previous equation. In other way we can write it lambda into f x k plus 1 minus lambda into f x k plus 1, where 1 minus lambda is equal to x minus x k divided by x k plus 1 minus x k. Thus, we see that any f x within the interval x k and x k plus 1 can be written as lambda k f x k plus lambda k plus 1 f x k plus 1, where certainly lambda k plus lambda k plus 1 is equal to 1, because we have just considered lambda k plus 1 as this one x minus x k divided by x k plus 1 minus x k, and lambda k would be is equal to 1 that is the 1 minus of this amount. Thus, we can say that lambda k plus lambda k plus 1 is equal to 1, alright. Thus, as we see that any function f x can be expressed as the linear function here. What is f x k? F x k is the functional value at the grid point x k. F x, that is the constant value certainly. F x k plus 1 is the functional value at the grid point x k plus 1, and here lambda k and lambda k plus 1, these are the unknown variables for us. Thus, we can say f x is being expressed as the linear function very nicely. Just we have considered one subinterval. If we extend this one, just like as we did for x, we have extended that for 3 grid points, and for r plus 1 number of grid points as we have done, the similar way we can do it for the r plus 1 number of grid points, and we can write down the function f x as summation lambda k f x k, k is equal to 0 to r, where summation of lambda k's, that is from r 0 k 0 to r is equal to 1. Individual lambda k's are all in between 0 to 1, and another condition is also there. Now, this can be written as summation k is equal to 0 to r lambda k f k. Rather, this is equal to lambda 0 f 0, lambda 1 f 1, in this way lambda r f r. Just see what we have done. We have again considered the functional values at the grid points x 0, x 1 up to x r plus 1 number of grid points. We have introduced the variables r plus 1 number of variables lambda 0, lambda 1 to lambda r in such a way that these two conditions hold together. Summation of lambda k is equal to 1 and individual lambda k's are in between 0 and 1, and again the same condition we have to impose here, that at most 2 lambda k's are non-negative, rather greater than 0, and if so they must be consecutive. Thus, this is the basic principle for handling the separable programming problem, that is any function which can be written in the form of separable, in the separable form, individual functions will just express in this way as the combination of the linear functions, and we will handle in the next. Now, what is the advantage in this procedure? And one thing I have forgot to mention, that this criteria is called the adjacency criteria, because this criteria is very much important when we will apply the simplex algorithm in the next. Now, coming back to the separable programming problem, where what is that? Maximize or minimize summation fi xi I is equal to 1 to n number of decision variables are involved, such that I is equal to 1 to n gij xi less than is equal to bj. There are m number of constraints are there, and xi's are all greater than equal to 0, I is equal to 1 to n. Now, by applying the previous procedure, each fi xi and gij xi, these are the nonlinear functions, and these are the functions of individual decision variables. Thus, this can be expressed as combination of summation of linear functions, just like before. Thus, this separable programming problem, and one thing is also there, that individual decision variables are bounded, otherwise separable programming problem technique is difficult to apply because we cannot partition the interval. Now, this can be written nicely in this fashion, that is maximize or minimize summation I is equal to 1 to n. Just see how I will write fi xi. Fi xi can be written as, I am introducing another index k here. There are r plus 1 number of grid points, that is why fi xi can be written as lambda ik fik. Clear? Thus, we can write down here I is equal to 1 to n, k is equal to 0 to var lambda ik fik, where fik is equal to functional value at the grid point xik. Xi is the decision variable and xik is the k plus 1th grid point. Thus, in the separable programming problem, the objective function can be expressed as the summation of the linear functions. This is a linear function. Thus, f1 x1 is a linear function, f2 x2 is a linear function. In this way, we will get a summation of individual terms where the terms are all the linear functions. Now, this is about the objective function. Let me come to the constraint, that is how I will express gij xi as the linear functions in the next. This is a nonlinear function again. Again this can be written as the combination of k plus 1 terms where individual terms are the linear terms, lambda r k, lambda I k, g I j k and x I k, all right. If this can be written as this, then certainly I can write down the constraint set as for the separable programming as summation k is equal to 0 to r, and there is another summation also is there, I is equal to 1 to n, and lambda I k g I j k, and this is less than is equal to b j, where j is equal to 1 to m. Not only that, there is another condition should be there, that is k is equal to 0 to r, lambda I k must be is equal to 1, individual lambda I k's are 0 to 1, where I k is equal to one thing. I should mention here that here you see our xi, for the decision variable xi, the grid points are x0i, xi0, xi0, xi1, xir, thus Ri. Thus, this is the number of partitions are say Ri, because for individual decision variables we can have partitions with different numbers. Not only that, which I should mention here, one thing is that the partition should not be, may not be equally spaced. It could be unequally spaced as well depending on the nature of the function. Thus, instead of partitioning the range of xi, we are partitioning with Ri plus 1 number of grid points. Okay? Grid points are there. Thus, here as well, the here this is I, this is I, thus this is I, all right. And here k is equal to 0, 1 to Ri, and I is equal to from 1 to n, because n number of decision variables are there. Okay. This is the equivalent form linear programming problem with of the original separable programming problem, and this can be solved with the simplex algorithm and imposing the adjacency criteria. Otherwise, the linear combinations we have considered, that is not useful. Now, this form, since we have introduced the lambda decision variables here, this form is called the lambda form, lambda form of equivalent LPP, all right. And this adjacency criteria means that in this decision, in this linear programming problem, when we will solve it with simplex algorithm, there will be a restricted basis entry rule will be imposed, and that is that at a time 2 lambda I k's can be, at the most 2 lambda I k's can be in the positive level, and that is, I can write down that this is the restricted basis entry rule for simplex algorithm. I will explain this further with numerical example, that then you can understand what I mean to say about the restricted basis entry rule. Now, similarly, instead of lambda form, we can have some other two forms as well for expressing any nonlinear separable programming problem with the equivalent linear programming problem. I am coming to that in the next. One form is the del form and another one is there, that is the delta form, that I am coming to the next. We are having the separable programming. Again consider the separable, originable separable programming in this way. Fi xi I is equal to 1 to n, subject to I is equal to 1 to n gij xi less than is equal to bj. See, we have considered here the approximations in this way. Let me consider the first interval xi0, xi1. How fx is being written here? I can write down fx minus fxi0 divided by x minus xi0 is equal to fxi1 minus fxi0 divided by xi1 minus xi0. Rather, I can write down fx as equal to fxi0 plus fxi1 minus fxi0 into x minus xi0 divided by xi1 minus xi0. Let me consider del fi1 is equal to fxi1 minus fxi0 delta fi1 and del I1 as x minus xi0 divided by xi1 minus xi0. If I am writing so, then fx can be written as fx is equal to fxi0 plus del fi1, that is a constant because we are considering the difference between the functional values in the consecutive grid points into del I1 clear fxi, alright, fxi. Now, if this is so, now you see here this delta I1 is in between 0 to 1. Thus, you see as in the lambda form we have introduced the lambda decision variable, and here we can instead of introducing lambda decision variable, we can introduce the decision variable del I1, alright. Similarly, for r plus 1 number of grid points, this can be generalized as fx is equal to fxi certainly fxi0 plus del summation k is equal to 0 not 0 1 to ri del f I1 ik del ik, and here delta ik less than is equal to 1. Now, instead of going for the lambda form, we can use the del form as well. One advantage here is that only one rule I can impose here, that only one delta ik is positive at a time, because x can be in any one of the sub intervals, and we have considered the proportion of the sub interval, and thus we can say this is the difference of the functional value in the consecutive grid points. Thus, while we will consider the linear programming problem, in that time the restricted basis entry rule we have to impose in the del form is that only one del ik would be in the positive level for all I. All right. With this idea, let me express the separable programming problem once more. Thus, I can write down the separable programming problem in this way: maximize or minimize summation individual functions can be written in this way: f x I 0 plus k is equal to 1 to r I del f I k, okay. And since there are n number of decision variable, this can be written as I is equal to 1 to n this, and subject to the condition I is equal to 1 to n and individual constraints function in the similar way I can write down g I j x I 0 plus summation k is equal to 1 to r I del g I j k. We will consider the constraint function at the individual grid points, and this is the del I k. This must be less than is equal to V j, j is equal to 1 to m. Here del I k is in between 0 to 1 for all I and k, and for solving above linear programming problem, we should impose restricted basis entry rule as at most one del I k must be positive for all I. All right. Thus, this is the we have achieved to the delta form of the delta equivalent form of separable programming problem. Now, there is another form, that is delta form. Let me write down that form as well, that is delta form. Here the consideration is little bit different, other things are same. As I have considered, that is f x as f x I 0 plus f x I 1 minus f x I 0 x minus x I 0 divided by x I plus 1 minus x I, x I 1 minus x I 0. Here we are considering some other decision variables. We are considering del f I 1 as f x I 1 minus f x I 0, and we are considering the difference of x as well, f x I 1 as x I 1 minus x I 0, and we are considering del I k as x minus x I 0. That is the only consideration here. So that f x can be written as, let me write down in general form, any f x can be written as summation of I is equal to 1 to n f x f I x I. This is equal to summation I is equal to 1 to n f I x I 0 plus delta, there will be a summation k is equal to 1 to r I delta f I k divided by delta x I k into delta I k. All right. One thing you just see, this is a constant here, because we are considering the difference between the functional value as the at the k plus 1th grid point and the kth grid point. This is the, we are considering the difference of the grid points only. This is also constant. Only the decision variable is del I k. And what is the value for del I k? Del I k can be, this is the value for del I k. Just see the range for del I k. As we know that in this case x in between in the first interval x I 0, x I 1. That is why x minus x I 0 must be in between x I 1 minus x I 0. Thus, I can say that del I 1 here, not k, here the index is 1, del I 1 must be in between 0 to del x I 1. Thus, I can say here del I k in between 0 to del x I k. Thus, you see this is the objective function. Similarly, we can write down the constraint function as well, and where the decision variables will be delta I k's, and this is in between 0 to del x I k, and these are all the constants. Now, whatever theory just we have, we got the same thing, we will just apply for the numerical example in the next. Let me consider this numerical example, that is the function of two variables, minimize x1 square minus 4x1 minus x2, and subject to the nonlinear constraint 2x1 square plus 8x2 square less than is equal to 30, and x1 is in between 0 to 2 as well x2. Now, this is a separable, we can apply the separable programming technique, because you see the function f1 x1 is equal to here x1 square minus 4x1, f2 x2 is equal to minus x2. Similarly, for the constraints g1 x1 is equal to 2x1 square and g2 x2 is equal to 8x2 square, and these are the bounds of x1 x2. Now, for handling this thing, either we can apply the lambda equivalent form, which is LPP, we can use the del equivalent form, in any one of these three we can apply. Let me go for the lambda form. Now, for doing this thing, we need to find out the functional values fi's and gij's at the grid points. Now, since the x1 is in between 0 to 2, I can divide the interval, I can partition the interval with 3 grid points 0, 1 and 2. Similarly, for x2 as well. Now, as I said, if we increase the number of grid points, then we will get the better result. Now, increasing number of grid points means we are doing the better approximation. Now, let me consider, since I am doing manually, let me consider the grid points as this one, k, x1k and x2k. That means we are considering the grid points. First grid point is 0, second grid point is 1, third grid point is 2. All right. Let me find out the functional values here. What we get? f1, f11, so that would be is equal to 0, f12, no sorry, this is f10, this is f11, f11 would be is equal to 1 square minus 4, that is equal to minus 3. Then functional value at point x equal to x1 equal to 2, we are having 2 square minus 8. Minus 4. All right. Similarly, we will go for functional values f2 at these grid points. We will get 0, minus 1, minus x2 is the point, minus 2. Similarly, go for G1k, G10 is equal to 0, G11 is equal to, at point 1 it is equal to 2, and at point 2 it is 8. Similarly, G2k is equal to 0, 8, 32, because this is the Z2 function. If this is so, we can write down the equivalent linear programming problem in this way. The objective function is minimize the form was summation I is equal to 1 to n, k is equal to 0 to r I, lambda I k, f I k. Here it is equal to minus 3 lambda 1 1, because lambda 1 0, lambda 1 1, lambda 1 2 we will introduce in this way, lambda 2 0, lambda 2 1, lambda 2 2, then it is minus 4 lambda 1 2, minus 1 lambda 2 1, minus 2 lambda 2 2. This is the objective function for us. And what about the constraint? Constraint would be subject to, this constraint we can write down as the combinations of this lambda 1 0 into 0, lambda 1 1 into 2, lambda 1 2 into 8 plus lambda 2 1 into 8 and 32 into lambda 2 2 less than is equal to 30. And what else? We are having the conditions. Condition, as we know, the condition is summation lambda I k's would be is equal to 1. Thus, we are having lambda 1 0 plus lambda 1 1 plus lambda 1 2 is equal to 1. Not only that, lambda 2 0, lambda 2 1 plus lambda 2 2 is equal to 1, and these decision variables are all positive. That is why the non-negativity constraint is satisfied. Just see, we are having the minimization of this linear programming problem, that is we can apply the simplex algorithm very nicely here. Let me formulate the table for the simplex algorithm. This is the equivalent linear programming problem for the given separable programming problem. As we see that here we are having 6 unknowns, lambda 1 0, lambda 1 1 and lambda 1 2. We are having one inequation, and to make it equation, because we want to apply the simplex algorithm, so we will introduce the slack variable x3 and we will get the equation 2 lambda 1 1 plus 8 lambda 1 2 plus 8 lambda 2 1 plus 32 lambda 2 2 plus x3 is equal to 0. Now, let us just formulate the simplex table in the next. The table 1, this is the simplex table for us, and we are calculating the Zj minus Cj value, since this is this is the minimum value, that is why we are accepting this. That's thus lambda 1 2 would be the should be the entering variable in the next table, and we should see which one is the outgoing variable, because that is more important. As we know the restricted basis entry, that in the set lambda 1 0, lambda 1 and lambda 1 2, there is another set lambda 2 0, lambda 2 1 and lambda 2 2. From here at the most 2 lambdas can be in the basis, and that must be consecutive. That is why this is acceptable, either lambda 1 0, lambda 1 1 would be in the basis, or lambda 1 1 and lambda 1 2 must be in the basis. But as we see, lambda 1 2 is the entering variable. If lambda 1 0 is the outgoing, then only it is acceptable, otherwise it is not acceptable, because 1 0 and 1 2 cannot stay together. As I have showed, that must be consecutive. Thus, as we see from the minimum ratio, lambda 1 0 is the departing variable, that is why this is quite acceptable to us, and this is a pivot element for the next table. That is why in the next basis we will have x3, lambda 1 2 and lambda 2 0. Again we will just apply the simplex algorithm here and we will go for the minimum of Zj minus Cj. Just look at this, Zj minus Cj value, here is the minimum minus 2. But if I consider minus 2 as the minimum, that means lambda 22 is the entering variable, lambda 20 must be departing, then only lambda 22 can enter, otherwise lambda 22 cannot enter, because 20 and 21, 22 these are not consecutive values. Thus, if we select lambda 22 as the entering variable, this must be departing variable, but this is not acceptable. Thus, we are proceeding to the next minimum, that is minus 1, and minus 1, as we see, minus 1 if lambda 21 is the entering variable in this case, thus we can accept it, and 1 is the pivot element. We are moving to the next, and here only one minimum is there, that is why we can select this as the entering variable lambda 22, and we will proceed to the next table, table 4, and the next table gives us the optimal solution like this. Alright, and since here Zj minus Cj all are positive, thus we can accept this as the optimal solution. Then what is the optimal solution for us? Optimal solution would be lambda 10 equal to 0, lambda 11 equal to 0, but lambda 12 is 1. But here lambda 20, lambda 21 and lambda 22, these are the values. Now these are the decision variable values for the equivalent linear programming problem, but we are more interested to get the original separable programming problem. That is why we need to convert this value lambda values to the x1 x2 values, then only we can say that is the corresponding optimal for the separable programming problem. As we know that x1 is equal to lambda 10 into x, lambda 10 into the 0 plus lambda 11 into 1 plus lambda 12 into 2, thus we get x1 is equal to 2. Similarly, we will get x2 is equal to 2, because x2 equal to 1.4375. How? Because this is lambda 20 into the grid point 0, lambda 21 into the grid point, the next grid point 1, and lambda 22 into the next grid point 2. If we just substitute lambda 21 and 22 value here, we are getting the value for x2 as 1.4375. Thus, we can declare this is the optimal solution for the original separable programming problem. Again, I should mention here, this is the not very exact solution, this is the approximate solution, because we made the approximation of the nonlinear function with the linear function, and if I want to have the corresponding optimal value of the objective function, we solved with the maximization problem. Now, we will go back to the minimization problem, and we will substitute this x1 value and x2 value here, and we will get the minimum value of function as minus 5.4375. That thus, we are getting the approximate minimum value for fx. Now, this is the technique for solving the separable programming problem. Separable programming problem is very efficient to solve the separable functions, nonlinear functions, and this idea can also be extended for the multi-stage programming problem. And this is this may be the local minima or local maxima depending on the condition of the function. If we go to the convex programming problem, that is a minimization problem if both the objective function and the constraint both are convex, then whatever local we are getting, that can be declared as a global. That idea holds true for this case as well. That is why if we are interested, we can go for the global maximum depending on the functional nature, that is the functions involved in the objective function and the constraints. And that is all about today. Thank you very much.